Astronomy is often full of some very confusing and odd terms. So is any tough subject for that matter. Consequently, this lesson will group and define some odd-sounding terms for you with respect to the measurements of our days, months, and years, and how they're related to the stars, moon, earth, and sun in order to try and make things easier. This lesson will use three key terms throughout we'll get to know. Sidereal, which is a term that implies we're using a distant star as a reference point. Solar or tropical, which is a term that means we've chosen the sun as a reference point. And synodic, which is a term relating the average time between conjunctions of two celestial bodies as observed from a parent planet. In this lesson, it involves the conjunction or meeting up between the sun and moon as observed from Earth. We'll see how this refers to units of time in astronomy, including days, months, and years. Let's begin with the most basic unit of time in this lesson, 1 day. What is a day to you? Likely you think of a day as something that's 24 hours long, the period of time between high noon today and high noon tomorrow, or the amount of time it takes the sun to appear on the meridian again. All are correct, refer to basically the same thing, and all use the sun as a reference point. Thus, a solar day is the time it takes for the Earth to rotate on its axis, so that the sun is in the same position in the sky as it was the day before, 24 hours. Your watch and modern societies run on solar time. The solar day is the basis for civil timekeeping. Contrast this with the sidereal day, the time it takes for Earth to rotate on its axis, so that distant stars appear in the same position in the sky as the day before. 23 hours, 56 minutes, and 4 seconds. Astronomers often like to use a sidereal day as opposed to a solar day because it tells them when a certain star will return to the meridian the next night, making it easy to spot. For us, however, it's important to note and explain the obvious. A sidereal day is shorter than a solar day. Why? This happens because the Earth orbits the sun as it turns on its own axis. Over the course of a day, the Earth will move about 1 degree on its year-long orbit around the sun. We get this by dividing 360 degrees in its orbit by about 365.25 days in a year. This means the sun appears to move on our sky 1 degree from west to east relative to the distant or quote fixed stars. Therefore, the Earth has to turn about 4 minutes more each day for 1 full solar day to occur. We get this number by dividing 360 degrees by 24 hours for 15 degrees in 1 hour, and thus about 4 minutes per degree. The next unit of time up from the day is the month. Just as per the days of our lives, there is more than one way to measure out the months of our lives. As per the sidereal day, we can use the stars to measure the orbit of the moon about the Earth. The sidereal month is the time it takes for the moon to complete a full orbit around the Earth with respect to returning to the same place among the stars, 27.32 days. But if we use the moon's conjunction with the sun as seen from Earth to measure the length of a month, then we get a synodic month, the amount of time it takes for the lunar phases to cycle through one time, and for the moon to return to the same position in the sky relative to the sun, 29.53 days. The synodic month is sometimes called a lunation or lunar month. A separate lesson on the sidereal and synodic month explains the details of why the synodic month is longer than the sidereal month. Annoyingly to the uninitiated, astronomy has 2 ways by which to measure the length of a year as well. The tropical year, aka the solar year, is the length of time it takes the sun to travel from and return to the vernal equinox, 365 days, 5 hours, 48 minutes, and 46 seconds, which is 365.242199 days. All I want you to understand for this lesson is that the solar year is a measure of the time it takes for the cycle of the seasons, covered in detail elsewhere. To repeat, the tropical or solar year is the basis for our calendar as much as the solar day is the basis for the length of our actual day. However, there is the other kind of year, the sidereal year, the time it takes for the sun to return to the same position in our sky with respect to the stars, 365 days, 6 hours, 9 minutes, and 10 seconds, or 365.256363 days. As with the days and months we went over, a discrepancy is clearly present between the solar year and sidereal year. The solar year is about 20 minutes shorter than the sidereal year because of an effect called precession, which is basically the wobbling of Earth on its axis with time. A solar day is the time it takes for the Earth to rotate on its axis so that the Sun is in the same position in the sky as it was the day before, 24 hours. We run our societies and clocks on the solar day as much as we run our calendar year on the basis of the solar or tropical year, which is the length of time it takes the Sun to travel from and return to the vernal equinox. 365 days, 5 hours, 48 minutes, and 46 seconds. Astronomers may have more use for using stars as a reference point for timekeeping, however. The sidereal day is the time it takes for Earth to rotate on its axis so that distant stars appear in the same position in the sky as the day before, 23 hours, 56 minutes, and 4 seconds. The sidereal year is the time it takes for the Sun to return to the same position in our sky with respect to the stars, 365 days, 6 hours, 9 minutes, and 10 seconds. And the sidereal month is the time it takes for the Moon to complete a full orbit around the Earth with respect to returning to the same place among the stars, 27.32 days. Sometimes the synodic month is a reference as well. It's the amount of time it takes for the lunar phases to cycle through one time and for the Moon to return to the same position in the sky relative to the Sun, 29.53 days. The synodic month is sometimes called a lunation or lunar month. Let's say you all of a sudden were plopped into the middle of nowhere with absolutely no phone, no watch, and just the clothing on your back. You are also told that you'll be rescued in 365 days, exactly at noon, and you better be exactly on time too. In such a scenario, what would you use to approximate the passage of time? The Sun, but of course the Sun. One of the fundamental units of time, one day, is related to the motion of the Sun. It's called a solar day, the interval between two successive appearances of the Sun on the meridian. Using the system of latitude and longitude on Earth, the meridian is like a line of longitude. In more simple terms, the solar day is a measure of the period of Earth's rotation relative to the Sun. Consequently, a solar day will be seen by you as the time that passes between high noon today and high noon tomorrow. A solar day has an average length of 24 hours. This lesson will explain what this has to do with mean solar time, apparent solar time, and the more famous standard time. What you may not notice by simply staring at the sky in desperation, counting time as you wait to get rescued, is that the length of the solar day changes during the year. That's because the Sun moves along the ecliptic at a varying rate throughout the year. The ecliptic is the apparent path of the Sun against the background of stars. The change in the solar day is subtle. There's only about a 1-minute difference between the longest and shortest solar day of the year. As you ponder this, you decide to look around for any supplies you can find to help you keep time. You get extremely lucky. You find a plain old working wristwatch. Such a watch keeps mean solar time, the time kept with respect to the average length of a solar day, or 24 hours. As you keep searching for more stuff, you find a sundial. All of a sudden, after being forced to stare at the Sun's path along the sky to keep time, you are flush with timekeeping options, but they're not all the same. A sundial keeps time according to apparent solar time, the time that's kept with reference to the Sun's actual position in the sky. If you were to stand there long enough, looking at your wristwatch and the sundial, you'd notice that their times would not be synchronized over the year. The difference between apparent and mean solar time can be over 15 minutes. The discrepancy between mean solar time and apparent solar time is known as the equation of time. This can really complicate your rescue's exact timing. Which option do you go with then? Let's think about this. The sun crosses the meridian at noon. The exact moment the sun crosses the meridian depends on a person's longitude. That's essentially saying that unless your rescuers are exactly north or south of you, their quote noon will not occur at the same time as your quote noon. That could totally mess up any rescue attempt. In order to overcome this problem, time zones were created. A time zone is an area of Earth about 15 degrees wide in longitude that has a uniform standard time. Standard time is the official time kept in a time zone, typically based on the mean solar time of the central meridian in each time zone. Since a time zone varies in longitude, based on what I said before, you should understand that even though your watch may read noon, it may not truly be the time the sun crosses the meridian you're on. But such sacrifices in accuracy of time have been made by people because the difference of actual noon versus that read by your watch is usually less than 30 minutes. Even 30 minutes is not a huge difference in apparent solar time, and so it's far more convenient to standardize time than worry about constantly having to adjust it with every little step east or west of your position. Overall, if your rescuers are in your time zone and using a watch, you can easily synchronize your rescue without having to adjust your watches or having to worry that your sundials are reading noon at different times based on small changes in longitude. A solar day is the interval between two successive appearances of the sun on the meridian. The length of the solar day varies slightly during the year because the sun moves along the ecliptic at a varying rate. The ecliptic is the apparent path of the sun against the background of stars. Consequently, people keep time using a fictitious sun, one that has a noon exactly 24 hours apart, regardless of whether the real sun is on the meridian at 12 or not. Thus, we run our civilization on mean solar time, the time kept with respect to the average length of a solar day, or 24 hours. This kind of time doesn't take into account the sun's true solar day length variations. Instead, we just use an average number throughout the year. This is different from how a sundial works, which is based on apparent solar time, the time that's kept with reference to the sun's actual position in the sky. The discrepancy between mean solar time and apparent solar time that ultimately arises is known as the equation of time. To make our ability to tell and synchronize time easier, time zones and standard time have been introduced. A time zone is an area of Earth about 15 degrees wide in longitude that has a uniform standard time. Standard time is the official time kept in a time zone, typically based on the mean solar time of the central meridian in each time zone. Are you a leapling? A leap year baby, that is to say? If you are, then you only get to celebrate your true birthday once every 4 years. Maybe you feel cheated at not having your birthday on February 29th every year, or maybe you don't care since you just celebrated the day before, February 28th, or after, March 1st, in a non-leap year, a year where February only has 28 days. You can thank events that happened thousands of years ago for cheating you out of a birthday on non-leap years. Or perhaps you can thank them for letting you have an ultra special birthday once every 4 years. Maybe you even feel younger because you have fewer birthdays, whatever tickles your fancy most. Anyways, this lesson will tell you how the concept of a leap year arose and why. A leap year, by the way, is a year that has 366 days as opposed to the usual 365. To understand why leap years exist, we first need to define a tropical year. The tropical year, aka the solar year, is the length of time it takes the sun to travel from and return to the vernal equinox. The tropical year is the same time it takes for the cycle of the seasons to repeat, and that length of time is about 365.242199 days long. That's 365 days, 5 hours, 48 minutes, and 46 seconds. See the lesson on the cycle of the seasons for more on what the vernal equinox is with respect to the seasons and the position of the sun. The length of the tropical year was estimated by the ancient Egyptians to be 365 days. That's pretty close to the actual tropical year, isn't it? These ancient whiz kids knew that the true length of the year was a bit longer than 365 days, however. That's because ancient Egyptians were excellent observers and figured out that over many hundreds of years, the Nile flood occurred later every year in a cycle lasting 1500 years. Since the ancient calendars, including the ancient Egyptian one, fell behind the true solar year, adjustments were made over the centuries by more than one calendar in society in order to try and weed out the inconsistencies between the actual length of the year and their calendars. However, it wasn't really until Julius Caesar's and Pope Gregory XIII's powerful ruling hands made a couple of decrees that the concept of a leap year in its modern form was born. Their actions led to the addition of an extra day every 4 years and the omission of 3 days every 400 years to match our calendars to the true solar year as best as possible. Why bother doing this? The lesson on the Julian and Gregorian calendars explains a bit more as to why this change occurred. But let's think of the alternative in this lesson. The alternative would be to use a calendar that has exactly the same number of days, hours, minutes, and seconds as the true solar year. In that case, let's say we start the next year at midnight. This year would end, by definition, 365.242199 days later, which would be just before 6 in the morning. This means that next year, each date would change not at midnight, but just before 6 in the morning. The year after that, each day would begin a little bit before noon, and so forth. If you're still confused as to why, good. That's exactly why we don't use such a crazy calendar and instead use the much simpler concept of leap years. Using the concept of a leap year, we give up the accuracy of any given calendar year compared to the solar year by a tiny bit for simplicity's sake. Nevertheless, even with such a system, the average length of each year when leap years are taken into account is basically the same as that of the solar year over a long period of time. Some years will be a bit too long, some a bit too short, but the average will be just right. A leap year is a year that has 366 days as opposed to the usual 365. We add an extra day to the end of February in order to achieve this. A leap year is added to try and match the average length of our years over a long period of time to the tropical year, also known as the solar year, which is the length of time it takes the sun to travel from and return to the vernal equinox. The length of the tropical year is 365 days, 5 hours, 48 minutes, and 46 seconds. Everybody knows where the equator, Arctic Circle, and Antarctic Circle are. The equator swings around Earth's belly. The Arctic Circle swings around the top of Earth, near Santa. And the Antarctic Circle, of course, is closer to the penguins of the South Pole. But what in the world are the Tropic of Capricorn and the Tropic of Cancer? This lesson will tell you what they are, where they are, and what their significance is to the tropical zone and the Arctic and Antarctic circles. Let's get right to it then. The Tropic of Cancer is a circle of latitude located approximately 23.5 degrees north of the equator, and the Tropic of Capricorn is a circle of latitude located approximately 23.5 degrees south of the equator. The area of Earth located in between the Tropic of Cancer and Tropic of Capricorn is known as the tropics, or tropical, or torrid zone. You know, it's the area of Earth that's really hot and lots of rainforests lie. The reason Cancer and Capricorn are part of their respective names has more to do with history than anything happening right now. In ancient times, when these lines were named, the sun was in front of the constellation Cancer in our sky during the summer solstice, and in front of the constellation Capricorn in our sky during the summer solstice. The summer or northern solstice marks the beginning of summer in the northern hemisphere and winter in the southern hemisphere. It occurs around June 21st of every year. The winter or southern solstice is the time winter begins in the northern hemisphere and summer begins in the southern hemisphere, around December 21st of each year. Due to precession, or the wobbling of Earth's axis with time, the Sun is no longer in these constellations during these times, but the names have stuck nonetheless. Okay, so what's the big deal with the tropics of Cancer and Capricorn anyways? What do they tell us? Well, the Sun never appears directly overhead at the zenith anywhere outside the tropics. The points on the Tropic of Cancer are the northernmost points where the Sun can pass directly overhead. This means that if you're located north of the Tropic of Cancer, the Sun will always appear south of the zenith. It is at noon of June 21st of each year when the Sun is directly overhead on the Tropic of Cancer, marking the beginning of summer in the northern hemisphere. On the other hand, the points on the Tropic of Capricorn are the southernmost points where the Sun can pass directly overhead. If you're somewhere south of the Tropic of Capricorn, the Sun appears to be always north of the zenith. And as you may have already guessed, on December 21st of each year, the Sun is directly overhead at noon on the Tropic of Capricorn, signaling the beginning of summer in the southern hemisphere. The tropical zone is thus the only area of Earth where the Sun can appear directly overhead, and it does so twice within this zone as it passes between its boundaries. Because the tropical zone receives so much more direct or concentrated sunlight compared to the rest of the Earth, it helps to explain why it is so darn hot over there. Contrast this with the area north of the Arctic Circle during the winter solstice and the area south of the Antarctic Circle during the summer solstice. These circles of latitude are both located at about 66.5 degrees north or south latitude, respectively. During the winter solstice, the Sun does not rise north of the Arctic Circle and does not set south of the Antarctic Circle. During the summer solstice, the Sun does not rise south of the Antarctic Circle and does not set north of the Arctic Circle. You would think that because each region receives a ton of sunlight during at least parts of the year, they should be really hot for at least half the time. But remember what I said about the importance of the tropics of Capricorn and Cancer. North or south of these circles of latitude, the Sun is never directly overhead. This means the sunlight hits the surface of the Earth at a really low angle the farther away from the tropics you go. Instead of concentrating solar energy onto smaller tracts of land, like a magnifying glass at the tropics, such a low angle of incidence spreads out limited solar energy onto larger areas of land, disabling the Sun's ability to properly heat the Earth in these areas, partially explaining the cold weather over there. Unless Santa can move the Tropic of Cancer north by quite a bit, he'll always be flying around in the cold as a result. The Tropic of Cancer is a circle of latitude located approximately 23.5 degrees north of the equator, and it lies in opposition to the Tropic of Capricorn, which is a circle of latitude located approximately 23.5 degrees south of the equator. The area of Earth located in between the Tropic of Cancer and Tropic of Capricorn is known as the tropics, or tropical zone, or torrid zone. The Sun never appears directly overhead at the zenith, anywhere outside the tropics. It's during the summer solstice when the Sun is directly overhead on the Tropic of Cancer. The summer, or northern solstice, marks the beginning of summer in the northern hemisphere and winter in the southern hemisphere. It occurs around June 21st of every year. Conversely, it's during the winter solstice when the Sun is directly overhead on the Tropic of Capricorn. The winter or southern solstice is the time winter begins in the northern hemisphere and summer begins in the southern hemisphere, around December 21st of each year. Remember, because the Sun is able to shine directly overhead in the tropical zone, it is able to concentrate its sunlight, like a magnifying glass can concentrate sunlight, onto smaller areas of land. This heats the land up quite a bit. At latitudes north or south of the tropics, the sunlight hits the Earth at lower angles, spreading out its limited solar energy onto larger swaths of land. This means the land is unable to heat up as much. I'm a very visual driver. In all honesty, I have serious problems remembering street names. Half the time, I don't even know what city I'm in, even if it's a neighboring city. I can hike out of the deep woods to the spot I need to get to without any maps or navigation equipment. But in the city, I'm as lost as a babe in the woods. This is why I thank Miss Yu, Parkinson, Easton, and Getting for inventing GPS, the Global Positioning System. I use GPS all of the time to help me navigate through a city, even one I've lived in for several years. But even if you're one of the few that doesn't rely on GPS technology to find something or someone, the NSA is probably tracking you with GPS technology anyways. So don't worry, one way or the other, you'll never be lost thanks to GPS. That reminds me, I need to go put my smartphone into a lead container as I write this lesson about what GPS is, how it works, and how it's used. GPS is a navigation system. That's really the essence of it. It's a system that allows for real-time positioning on or near the surface of the Earth with great accuracy. That accuracy is said to be within a few meters. Such accuracy doesn't explain how people drive into lakes and rivers and blame their GPS for it. I'm as lost for an explanation for that as I am when my GPS frustratingly sends me to a post office when I should have been directed to a store. That being said, GPS is probably the best example of geodesy there is. Geodesy being the branch of applied mathematics that deals with the shape and dimensions of the Earth and the positioning of geographical points. The geocentric Earth-fixed coordinate system GPS uses is known as WGS 84, which stands for the World Geodetic System. The U.S. Air Force ensures that at least 24 GPS satellites are online all of the time to allow the system to operate fully. These satellites are in almost circular orbits over 20,000 kilometers above the surface of the Earth with a period of revolution that's almost 12 hours long in one of 6 orbits. This provides worldwide coverage for all of your GPS-enabled devices, courtesy of the U.S. The only currently viable alternative to GPS is the Russian version of GPS called GLONASS. I'm sure the Russians don't use it to spy on anyone. Regardless, a GPS satellite can send a radio signal that relays its location and time. This signal travels through space at the speed of light, reaching the GPS unit you use. This GPS unit receives the signal's information, notes the time of its arrival, and then calculates its distance from at least 4 satellites. Using geometry, the GPS unit can then figure out where it's located on Earth in 3 dimensions. And now for the fun part. What is GPS used for? I don't think it's possible to list everything it's used for in one lesson, but we can cover some things. Your smartphone almost certainly has GPS-enabled technology, which is in turn used by plenty of apps. GPS can be used in aircraft and maritime navigation, and maybe you still use a standalone GPS unit in your car for just such a thing. That unit can not only tell you where you are, but also how fast you're driving. This must be why the GPS lady yells at me to get out of my car if I'm driving too fast. Handheld GPS units are also great for hiking. Unlike the mysterious world of dating, you'll always know where you stand with someone if they have such a unit. GPS can be used by surveyors, military personnel for the conservation of nature, improving agricultural yield, tracking endangered animals, banking, and so much more. It's truly an amazing technology. You see, everyone loves and uses GPS, even pirates, because GPS tells them where they are. GPS, the Global Positioning System, is probably the best example of geodesy. Geodesy being the branch of applied mathematics that deals with the shape and dimensions of the Earth and the positioning of geographical points. The geocentric Earth-fixed coordinate system GPS uses is known as WGS 84, which stands for the World Geodetic System. GPS is a worldwide system that's maintained by the U.S. government. It involves over 24 satellites high above the Earth, sending signals at the speed of light to GPS units worldwide. Units which then use these satellites to figure out their location on Earth in 3 dimensions.
Hello everyone. I'm your tour guide, Star. Welcome to Out of This World Tours. Today's unique tour of the solar system includes breathtaking views of the 4 inner planets, commonly called the terrestrial planets: Mercury, Venus, Earth, and Mars. So hop on board my ship and come with me for a ride. As we start our trip, let me share some solar system background with you. Our solar system consists of 8 planets that are divided into 2 parts: the inner planets that we are visiting today, and the outer planets known as the gas giants. You can visit those on one of our other tours. There are a number of differences between the inner and outer planets, aside from location. The inner planets are small, dense, and composed mostly of rock, while the outer planets are composed mostly of gas, with no solid surfaces and only liquid cores. The inner planets also have few or no moons and no rings circling them, while the outer planets often have dozens of satellites and rings composed of particles of ice and rock. Wow, that travel time went fast! We're already arriving at the closest planet to the Sun, and our first stop, Mercury. The name Mercury comes from Roman mythology, where Mercury is the god of commerce, travel, and thievery. The planet probably received this name because it moves so quickly across the sky. Mercury is the closest planet to the Sun, and the smallest planet of our solar system. It is only 5% of Earth's size. This small planet looks very much like Earth's moon, and it is even a similar grayish color. It has no moons of its own, and, comprised mostly of iron and nickel, is one of the densest planets in the solar system. Mercury has a very thin atmosphere that keeps heat neither in nor out, so it is burning during the day, up to 430 degrees Celsius, and freezing at night, as low as minus 187 degrees Celsius. These temperature ranges are the most extreme in the solar system. Each day on Mercury lasts as long as 58 days and 15 hours on Earth, and a whole year on Mercury is only 88 Earth days. Although Mercury is often visible with binoculars or even the unaided eye, it isn't very interesting to look at because it has few geological features other than impact craters. Now on to our next stop, the second planet from the Sun. I'm talking about Venus. Venus is named after the goddess of love and beauty. It was probably named this because it is the brightest of the planets known to the ancient astronomers. As a matter of fact, Venus is often called the morning star because, with the exception of Earth's moon, it's the brightest object in the sky. Venus is known to many as Earth's twin because the 2 planets are very similar. Venus is 80% of Earth's size. Both have few craters, an indication that their surfaces are young, and their densities and chemical compositions are similar. There's also evidence that Venus once had water on it, but the water has boiled away with the extreme heat. In important ways, though, Venus is very different from Earth. Venus is the hottest planet in the solar system, with temperatures over 400 degrees Celsius. Its atmosphere is a thick cloud of various gases, including carbon dioxide, which traps the heat and transforms the planet into a furnace that is hot enough to melt lead. Venus's surface is actually hotter than Mercury's, even though it is farther away from the Sun. The length of a day on Venus is 243 Earth days, and a Venus year is 224.7 Earth days. Yep, you heard that right. A day on Venus is longer than its year. Very strange. Venus is also different in that it rotates backwards. All the inner planets in the solar system rotate counterclockwise when you look at them from above, but Venus turns clockwise. Time to leave this strange planet and visit your home planet, the third rock from the Sun, Earth. Since you all know Earth so well, our stop here will be short. Earth is the third inner planet and the one we know best. Earth is the only planet whose English name does not derive from Greek or Roman mythology. Earth is the largest and densest of the inner planets, and is the only place in the solar system where life is known to exist. Earth's atmosphere protects the planet from the dangerous radiation and helps keep valuable sunlight in, allowing life to survive. Earth is the only terrestrial planet with a large satellite, the Moon. Now we're off to the last stop on our tour, Mars. Mars is the final inner planet, named for the god of war. It is also known as the Red Planet, due to the rust of iron-rich materials that form the planet's surface. Mars is smaller than Earth and Venus at only 10% of Earth's mass. Mars's thin atmosphere has led some astronomers to believe that water that once existed on the planet might have actually leaked into space. One Mars day is nearly identical to a day on Earth at 24 hours and 37 minutes, and its year is 687 Earth days. Mars is cold with an average temperature of minus 55 degrees Celsius. The planet has two small moons that are thought to be asteroids captured by Mars's gravity. One of Mars's best-known features is its network of canyons that led many to believe there was once water and therefore life on Mars. Mars has huge volcanoes, the largest of which is named Olympus Mons. Well, that's it for our tour. We now head back to your home planet, Earth. On our way back, let's review the planets we visited. Mercury, closest to the Sun, smallest planet in the solar system, most extreme temperature ranges of all the planets. Venus, second from the Sun, often referred to as Earth's sister or twin. A day on Venus is longer than a year. Rotates clockwise, unlike every other inner planet in the solar system. Earth, third planet from the Sun, only planet known to support life. Only terrestrial planet with a large satellite, the Moon. Mars, fourth planet from the Sun, used to have water on its surface, has two small moons. Well, here you are, back safely to your home planet. Hope you enjoyed the trip. Hello, my name is Star. Welcome to Out of This World Tours. Today's unique tour of the solar system includes breathtaking views of the four outer planets, commonly called gas giants: Jupiter, Saturn, Uranus, and Neptune. We'll also visit the dwarf planet Pluto, so hop on board my ship and come with me for a ride. It is a bit of a journey to get to our first stop. While we're traveling almost 1 billion kilometers, depending on where the two planets are in their orbits, let me give you some of the history of this area. Our solar system consists of 8 planets, 1 sun, 1 dwarf planet, an asteroid belt, and many moons. The Sun is in the middle of our solar system. Next come Mercury, Venus, Earth, and Mars. These are the small and rocky inner planets known as the terrestrial planets. After Mars, there is an asteroid belt that separates the inner planets from the outer ones. The outer planets are called the Jovian planets, meaning huge gas giant. These planets in order are Jupiter, Saturn, Uranus, and Neptune. Pluto comes after Neptune, but it is no longer considered a planet. It is now a dwarf planet. Size is the most obvious difference between the inner and outer planets. The outer planets are huge. Our largest inner planet is Earth, and Earth is only 1/4 the size of the smallest outer planet, Neptune. The inner planets are rocky, sometimes all the way to their core. Gas giants are made mostly of gas with a non-gaseous core. Scientists haven't been able to discover exactly what exists in the core of a gas giant. They believe it may be solid or made of liquid metal. Hold on, we're traveling through the asteroid belt now, and the ride gets a bit bumpy. Finally, that's over. Look, here we are at our first stop, Jupiter. Jupiter is the first of the outer planets in order. It is also the biggest, with a mass that is more than all the other planets combined. Jupiter is so big that it often changes the trajectory of passing comets, and thereby protects the inner planets from being hit by them. Jupiter spins very fast on its axis, so one day there is short, only 10 Earth hours, but its year is quite long, nearly 12 Earth years. Look out your window and check out those colorful bands. The pattern of wide and narrow bands you see are made of whirling clouds. Jupiter also has very faint rings and at least 50 moons, probably more. Wow, what a great place to visit! The next stop on our tour is Saturn. Most people know Saturn for its rings, which are the brightest rings in the solar system. Many people don't know that Saturn is also a windy place, with winds at its equator that get up to 1,100 miles per hour. Saturn also boasts 50 moons, including Titan. Titan is bigger than the planet Mercury and is so large it has its own atmosphere. A day on Saturn is 10 hours, 39 minutes, and a year lasts 29.4 Earth years. All right, enough about this wonderful ringed planet. Off we go to planet number 7. Uranus looks different than the other planets, as you can see. It is tipped on its side. Scientists aren't sure why it is tilted, but they think it may have been hit by a large object, possibly a planet, a long time ago that caused it to tilt. Another theory is that the gravity of its large moons is pulling it over to its side. Uranus was discovered only 200 years ago, and it is hard for scientists to study because it is so far from Earth. Scientists do know it has narrow, dark rings, is 4 times the size of Earth, and has at least 27 moons. A day on Uranus is shorter than an Earth day at 17 hours, 14 minutes, and its year lasts nearly a century at 84.3 Earth years. When they were first studying Uranus, scientists noticed that its orbit was different than what they expected. They thought this might be due to the gravity from another planet, so they started looking for one and found Neptune and Pluto. So that's where we're going next. Ladies and gentlemen, look out your window as we arrive at Neptune. You probably know Neptune is a blue planet, but you might not know the blue color is caused by the methane gas in its atmosphere. Neptune is also the windiest planet, clocking wind speeds of up to 2,000 kilometers per hour. Scientists haven't studied Neptune much because it is so far away that it is hard to get information about it, and scientists have only once sent unmanned ships to visit it. Scientists do know that as the farthest planet from the Sun, Neptune is very cold. It is also the smallest of the gas giants, a little smaller than Uranus, and has surface gravity like Earth. Neptune revolves around the Sun once every 165 Earth years, and its day is around 16 hours, 6 minutes. That nearly completes our tour of the outer planets. But first, take a look out your window at Pluto. Poor Pluto. No one knows quite what to do with Pluto, but they've kicked it out of the category of planets and classified it as a dwarf planet. Some scientists think Pluto is one of Neptune's satellites that was pulled out of orbit. Others think it might be a double planet with its moon Charon. Pluto is made of half rock and half ice, so if it were closer to the Sun, it wouldn't have survived. It would have melted and become a comet. Pluto has a weird orbit that causes it to move in front of Neptune every couple of years. That will complete our tour of the outer solar system planets. On our way back to your home planet, I'll be reviewing some of the fascinating facts you heard about today. Jupiter is the fifth planet from the Sun and the largest planet. It has colorful bands and at least 50 moons. Saturn, the sixth planet, is known for its rings. It has at least 50 moons, including Titan, which has its own atmosphere. Uranus is the seventh planet, 4 times the size of Earth, and is tipped on its side. Lastly, Neptune, the eighth planet from the Sun, is the coldest planet and known for being blue. Pluto, now known as a dwarf planet, sometimes closer to the Sun than Neptune. I hope you enjoyed yourselves, and I look forward to seeing you on one of our other tours.